Okay, hello everyone, and thanks for the introduction. And I'm Hsu-Chieh, who it is a joint work with my PhD advisor, Stephen Smith. And the problem we deal with is about how to help schedule-driven traffic control to cope with the larger traffic volumes. And it is today's outline. First of all, I would like to introduce what is the schedule-driven traffic control. And schedule traffic control is a new development based on online planning and to solve the traffic signal control problem. And also, it's a fully decentralized approach. And in this approach, we treat each intersection as a single machine scheduling problem. And we just cluster those adjacent vehicles together as a clusters, or you can call it jobs. And we use this aggregate representation to represent those classes, to represent the cluster, right? And then we allow each intersection to communicate with each other by exchange those representation. And yeah, and so for example, if we have two competing traffic flow here, flow 1 may represent the north-south direction, and flow 2 may represent the east-west direction. And because of the clustering, we have a bunch of clusters here. And our goal is to minimize the cumulative delay. And the definition of the cumulative delay can be represented by this formula, because we know the arrival time of each clusters. And also, we know, after scheduling, we know the schedule time of the cluster. And also, we know the number of a vehicle within each clusters. So we can write down this kind of definition of delay. And this approach has achieved a very excellent performance in our field test. However, from our simulation evaluation, we do observe one problem under the highly congestion scenario. So the problem is that when the traffic becomes heavier, the distribution of the cluster size will shift from left to the right. Which means that under high congestion scenario, we may have a larger cluster with a higher probability. And sometimes we even get a very single large big cluster to schedule. So it may damage the efficiency of the schedule-driven traffic control. And under the high congestion, the problem becomes less of a scheduling problem and more of a how to manage those queues efficiently. So we need a composite approach to address this issue. So the most intuitive way to solve this problem is that we can just serve those clusters associated with a longer queue as soon as possible. And so we need to come up with a way to bias the scheduling search when the queue becomes larger. Yeah. So here we adapt the low complexity scheme, which is we just weight each clusters based on their queue length, associated queue lengths. So we can modify the definition of the delay to this form. So for example, if we have a shorter queue here, we just assign a smaller weight to those clusters. If we have a larger queue here, we just assign a larger weight to those larger clusters. We hope those clusters can be served as soon as possible. So that's the basic idea. And so based on those modifications, so the original scheduled traffic control problem can be turned to the weighted single machine scheduling problem. And further, if we want to solve this problem for a network, the problem will be how do we design this weight for a network. And in the communication or networking community, they already studied this problem very well. how to manage those queues. So the well-known algorithm should be the max-way scheduling, or we call it backpressure. We have several independent state, and we should choose which state to serve first. We can just based on their associated queue length. And it is another version, a stochastic version of the backpressure. And those approach can guarantee the queuing stability. And in the transportation and the physics, even the AI, the traffic congestion are well discussed. So before diving into our main algorithm, I would like to summarize our contribution. Yeah, this is the first hybrid approach combining the schedule-driven traffic control and the queue management. And it provides a queue management for the schedule-driven traffic control, and also it provides certain theoretical guarantee of queuing stability. And the most interesting part is that it has certain physical interpretation. So from our observation, we do observe several characteristics of the wave function. So what kind of characteristics we should provide for the wave function? The first one is when the queue are empty or even balanced. Balanced means that the queue lengths are comparable. We hope under this scenario, the scheduling will dominate the performance. On the other hand, if we have an unbalanced queue, but we don't want the impact of the smaller queue reduced to 0 in case that we have a larger cluster approaching the smaller queue. Yeah, we still want this larger cluster to be served as soon as possible. So based on these two characteristics, and we can just probability distribution may be a good choice here. If we use probability distribution, so the problem will be which distribution we should use. So in statistical physics and graphical model, Boltzmann distribution is a way to describe a large particle system, and it's a joint distribution of a larger system. So here we can just take each intersection as a particle, and each intersection has two states, like a north-south direction and the east-west direction. And once we have this kind of setting, we can write down the joint distribution through the Boltzmann distribution. And now the question will be how to derive the marginal distribution of each particle over each intersection here. Yeah, so what is the probability of phase 0 of this intersection? What is the probability of phase 1 of this intersection? And we only need to define our energy function, and then we can just write down the joint distribution. And you can observe here, the energy function has two terms. The first one is the local potential energy, and the other one is the interaction between two intersections. So once we can define those terms, we can just write down the joint distribution and then calculate the marginal distribution of each intersection. So here I give you some basic idea how the energy function is defined. So for example, if the difference between difference of the queue size between the blue queues and the orange queues become larger, we will prefer the north-south direction. On the other hand, we will prefer the east-west direction. So that we can use this difference to as our local potential energy. On the other hand, if this approaching queue become larger, it means that the interaction between these two intersections become attractive. And on the other hand, if this queue become larger, it means that the interaction become repulsive. They repulsive with each other. So once we have this kind of idea, we can define our energy function based on the Q. And so the question will be, how do we derive the marginal distribution? As you know, derive the marginal distribution based from the Boltzmann distribution is an NP-hard problem. So here we turn to the approximate inference here. And the final result, well, you can see that the wave function will be a soft-max function of the effective Q, and in which effective Q is equal to the local Q plus your upstream Q and minus your downstream Q times the weight of your neighbors. So it is a recursive form. So once we calculate this wave function, we can just apply it on each cluster. And in above cases, I just deal with the two-phase scenario, but we can extend our idea to the multiple phases without any hesitation here. Just like how do we extend the Bernoulli to the multinomial here. And because this recursive form, we can develop a messaging passing protocol to calculate the weight in real time. It's just, in this protocol, each intersection just needs to send out its Q length to its neighbor, and also its calculate weight to neighbors. And because in our approach, we adapt a similar policy as the back pressure, and back pressure can guarantee the Qing stability. So in our approach, we can also provide a similar stability by just provide an upper bound for the summation of Q. And in our simulation result, we test a 24 intersection model in the VSync traffic simulator, and we compare with our original schedule-driven traffic control. And the second one is we only apply the local Q. Local Q means that we only use this term to calculate the wave function. And the third one is we plus the upstream Q and the downstream Q. And you can see that the performance, the average delay can be improved further by adding on more information, Q information. And when we test our approach under the low traffic demand and the median traffic demand, you can see that under these two scenarios, the scheduling will dominate the performance. However, when we have a higher traffic demand, the queue management will dominate the performance. So it means that queue management is really working for the high traffic demand. And if we plot the distribution of the delay, we can also observe similar phenomena here. And for our extension of multiple phases, and it still provide further improvement. And if we record the average queue length and the average cluster size for each intersection, and for this most congesting intersection, we do observe a fair amount of reduction of the average queue length and the cluster size. For example, this is 33, and we can reduce it to 6. And yeah, the cluster size is similar. And in our initial field test result, this approach can still provide certain improvement for the PM rush hour. Okay, so to conclude, we provide a hybrid approach to integrate the stability into the schedule-driven traffic control, and especially under the heavy traffic scenario. And the algorithm is fully decentralized, so it can be aligned with the original schedule-driven traffic control very well. And it's a messaging passing protocol. And our future work will be, because currently I just relax the transportation network into a independent node. And the future work will be, can we use other decomposition of the graph to solve this problem? And the other one is, can we provide another way to ensure the network stability for a scheduling system? Yeah, for example, like can we provide another algorithm to cluster those to cluster those vehicles, or we can use different objective to do the optimization. Okay, thank you. That's all.
Thank you. So, I have a few minutes for questions, curiosities. Nothing? Yeah, please.
What kind of approximation approach you have used to get the joint distribution?
I use a simple Ising model. So I just, for example, in our original model, we just we use like a grid-like network, and in my approximation, I just take it as an independent node here. Yeah.
So, yeah. I'm not very sure how relevant it is, but in distributed constraint optimization community, people have used expectation maximization algorithm to get this joint distribution by using a decentralized approach. So maybe we can take a look on that.
Okay. Okay. Thank you.
Maybe I missed it. Your results had this clear improvement over previous work, but do we know how close we are to optimal?
The question will be, how do we define the optimal? Yeah, but yeah. I do compare with other traditional traffic signal control algorithm like a SCOOP or SCAT. Yeah.
You could do something clairvoyant with, knowing what the simulator is going to produce.
Yeah.
As an upper bound on performance.
Right.
Yeah, that would probably be better.
Yeah. Yeah. I will think about how to define the optimality of.
Super exciting.
Thank you.
I have one curiosity. Is there any minimum level of demand for which your approach is worth it to be applied? So that's when the problem is really worth it to be handled as a queue management problem. Have you studied this minimum threshold of demand, or?
You mean minimum threshold or something? Oh, by the way, our approach, this approach is one characteristic is that it has some smooth transition from scheduling to the queue management. So we don't need to use any parameter to to switch between
Just last question. Now about to have this different pattern of the traffic, like high level traffic next low level. So what's happening in this case? I mean, if it could be.
Oh.
How can you react to this?
Yeah. I see. Actually, for this result, I just test. For example, initially we have a small traffic, and then turn to heavy, and then turn back to small. So it has some kind of transition there. Yeah.
Okay. Thank you very much.
Thank you.